Okay, so let's see an application of this interpolation technique. An application due to Riesz about the boundedness of what we know called the Riesz projection. All right, so we're going to be working on LP of 0, 1, and we're going to be working with Fourier series. So we're considering the map, and so there's a tiny bit of complex analysis here, but very little. More complex numbers than complex analysis, really. So we're considering the exponential of 2IP pi and t for n in z, and these you might know from Fourier analysis or even from analysis 2 that they form a orthonormal basis of L2 of 0, 1. So that's a little fact that we're gonna need to remember. So En is an orthonormal basis of L2, right, of 0, 1. If you don't remember that or you haven't seen that before, just take that for granted. That's not really our point here to do this kind of Hilbert space analysis or Fourier analysis, really. But our point is to show that this map will extend to a bounded map on all of the LP spaces. That is the content of this theorem proved by Riesz in 1927, and that theorem is somehow the starting point of Fourier analysis as we know it since the 20th century. So why is that a starting point? Because really what Riesz theorem tells us is that an extremely simple infinite dimensional version of a diagonal matrix gives rise to a bounded map on LP, and then you'll get all sorts of other bounded map from the boundedness of that very simple diagonal matrix. Now, why do I call that a diagonal matrix? Let's have a look at the definition. The Riesz projection takes the Fourier series of a function, so the decomposition of a function into that basis, which is indexed by all integers, and restrict it to just consider those coefficients that comes from the natural number. So the way you should think about P is it's a diagonal matrix with respect to the basis En, which has 0 on the first infinitely many coefficients corresponding to negative reals, and then ones after that, right? It's an infinite dimensional version of that. So once you know that such a operator corresponds to this coefficient is continuous on LP, you can build from that and get the continuity of all sort of other maps. Just a little aside here, Fourier analysis or its generalizations that are sometimes called harmonic analysis play a key role in partial differential equations. That's because, well, what happens if you differentiate En? If you differentiate En, you're just multiplying it by 2I pi n. So differentiation operators will be, from a linear algebraic point of view, diagonal maps with respect to the Fourier basis. So Fourier analysis is about diagonalizing, from a linear algebraic point of view, differential operators. And if you know what sort of matrices gives rise to bounded maps on LP, and that's exactly what the techniques we're discussing now can give you, they will tell you how different functions of differential operators gives rise to maps that are bounded on LP. Let's put it in a different way. It will tell you when you have a mapping that maps, say, a data to a PDE problem to a solution of a PDE problem and preserves the LP norm of the data when you pass to the solution. So a lot of questions in PDE about which norms are preserved under solving a problem boil down to question in harmonic analysis about which maps are bounded in LP. And the very fundamental example of such an LP boundedness result is the theorem of Riesz, right? The simplest possible map on Fourier series that just projects down to those Fourier series that have only coefficients in the natural numbers as opposed to all of the integers. This map, which is obviously bounded in L2, I mean in L2 it's an orthogonal projection, is actually bounded in LP for all values of P. And the proof that we're going to give, which is due to Buckner, is it's a very smart use of interpolation, right? We're going to use the fact that we know it's bounded in L2, get that it's bounded on L4, and then deduce that it's bounded for all values of p between 2 and 4, and then do an induction argument and a duality argument to conclude the proof. So it shows really how the functional analytic techniques that we have been discussing interact with more concrete analysis to give more concrete result. Okay, so let us prove the boundedness of the Riesz projection. Let's start with an f in LP. I'm going to take an f that is a finite trigonometric polynomial. So I'm going to take an f of that form, n running between minus capital N and plus capital M for some n. Now that is a special kind of f that belongs to all of the LP spaces, in particular belongs to L2. Now I already know that P is bounded on L2, and I know that L2 intersected LP is dense in LP. So if I show that there exists a C, obviously independent of F, independent of N, such that P of F is smaller than C, norm of F, then I would have the fact that my operator P has a unique extension as a bounded linear map to LP. So I only need to consider these finite sums, but I need to prove a bound, an LP bound on the norm of P of F that's independent on capital N. Okay, now I can also, without loss of generality, assume that F inner product with E0, which is really just the integral of F from 0 to 1, is 0, right? Because that is just a constant. So I could add or subtract a constant to my F, because P is a linear map. It's not going to change the fact that P is bounded on LP or not. So without loss of generality, I can assume that. And so we have that P of F is the sum starting at 1 up to capital N of my, I'm not going to take capital N equals 0. I'm going to send capital N to infinity eventually. And that it's a sum from little n equal 1 to capital N of the decomposition of F into the trigonometric basis of L2. Okay, so I'm looking at such a P of F. And now an interesting realization is that that's more than a remark. So it's something that we should note, is that the integral of P of F raised to whatever power you want, let's call that M, is gonna be always equal to 0 for all M in N. And why is that? That's because P of F of M, right, if I raise such a sum to the power M, is going to be of the form a sum that can only start at 1 and goes to, further than capital N, but to some finite number of P F M E N, because, okay, whenever I multiply these ENs together, I get one that is further up in terms of the natural number indexing it, right? En times em is en plus m, because en is an exponential of 2i pi n t. So because of that, you cannot go back below n equal 1 just by multiplying these series with itself, whatever many times you do that, right? And because en is an orthonormal basis, you can decompose back into that basis, and you will not pick up any coefficient for n equals 0 or n negative by multiplying together ens for n positives. Right, but that means this has no E naught component because f had no E naught component, and the integral of PFM is, well, it's also equal to the inner product of PFM with E naught. Right, and if all of your coefficients, if the decomposition of PF to the M doesn't have a coefficient in front of E naught, then its inner product with E naught is 0 because the En form a orthonormal basis. So what we have is, because we start without loss of generality, with a function that has mean 0, the mean of all of the powers of pf will also be 0. Right, now we're going to exploit that through something that might look a little strange. I mean, this proof is a bit too clever for its own good, but okay, if you know the history, you realize that there's some good reasons to understand that, but the reasons are coming from complex analysis, so I'm hiding them a little bit. P can be written as 1/2 of the identity map plus I times a map T that we call the Hilbert transform, and T is minus I times the sum from n equal minus n to n of f e n multiplied by the sine of n. So for the positive n you just keep it as it is, but for the negative n you multiply by minus 1 en. Alright, so that's just a variation on the Riesz projection, but that allows us to decompose the Riesz projection up to a factor 1/2 as the identity plus a similar linear map. And now when I raise that to the m, especially if m is say twice an integer, I can expand the sum of f plus itf. And so what do I get? I get, let's keep that, for any k in n star, well, the integral of f plus itf raised to the power 2 to the k has to be 0. And that tells me that for every k in n star, if I expand that sum, the sum from L equals 0 to 2k of, what have I got? I raised to the power 2k minus L times, choose L, times the integral of f raised to the power L times t of f raised to the power 2k minus L has to be 0. And this strange looking equality is going to be the key to the argument. Okay, so in order to exploit that, we have to realize that, well, we're dealing with real valued function, right? Our f of t belongs to R for all t. But what is f of t? Right? It's the sum n equal minus n, capital N to capital N of f in a product with en times exponential, so times cosine nt plus I sine nt. And now if you reorganize those things, what do you get? You get that this is the sum n equal 1 to n of f comma en plus e to the minus n times the cosine nt, and then plus in the imaginary part I times the sum n equal 1 to n of f comma en minus e to the minus n times the sine of nt, right? And this here, and this is a real number, this times this is a real number, so this here has to be a real number. But what we've got here is really is really t of f actually. So what we get is that t of f of t has to be real for all t in 0, 1. So that's the point. That's one of the point of introducing that Hilbert transform. The Hilbert transform of a real valued function will still be a real valued function. So in this expansion that we have here, both f and t of f are real numbers, and this is to be equal to 0. So the only way it can be equal to 0 is if both the real part and the imaginary part are equal to 0. So taking real part in 1, what do I get? I get that for every k in n star. The real part correspond to choices of L that are of the form 2 times something. So let's say j running between 0 and k of I to the power 2k minus 2j, which is minus 1 to the power k minus j, 2k, which is 2j, integral of f, L is no 2j t of f to the power 2k minus 2j. This has to be 0. And now I'm going to reorganize that, putting on the other side the case j equal to 0. And what will I get? I would get that for all k in n star, minus 1 to the k. Okay, I'm bringing it so minus 1 to the k. Well, let's keep it like that. Minus 1 to the k times the lk L2k norm of tf raised to the power 2k has to be equal to minus the sum j running from 1 to k of minus 1 to the k minus j 2k 2j times this integral f 2j tf 2k minus 2j. Now, why is that helpful? That's because it's allowing me to express the norm of t of f in L2k using information on the norm of f and t of f on LP for values of p below 2k. So in particular, right, if you were to take k equal to 2, that would give you information on the L4 norm based on information on the L2 norm of t of f, and we already know quite a bit about the L2 norm. So how are we going to exploit that? We're going to use Euler with appropriate exponents. So let's use Euler with p being 2k divided by 2k minus 2j, and we're going to apply Euler in this integral and see what we get. So the point of choosing this exponent p is that we're going to raise tf here to the power 2k minus 2j times p, so we're going to raise it to the power 2k. So we're going to be comparing the L2k norm of tf on the left hand side to the L2k norms of tf on the right hand side and get a bit of an induction relationship. So what we get by doing that, okay, we take p equal this, so what should our p prime be? Our p prime should be 1 minus 1 upon p, which is 2k divided by 2k minus 2k minus 2j divided by 2k, which is 2j divided by 2k. Okay, so j over k is our 1 upon p prime, so p prime is k over j. Cool. Applying Euler then gives me that tf of 2k raised to the power 2k has to be smaller. Let's forget all those signs. Sum j equal 1 to k. This number times, okay, what does Euler gives me? It gives me t of f in L2k norm, and then this is raised to the power 1 upon p times 2k, so this is raised to the power 2k minus 2j, and then my f, the 2j gets multiplied by 2k divided by 2j, so I get the L2k norm of f, and this is being raised to the power 2j. Great. Now what I'm going to do is I'm going to divide both sides by the L2k norm of f raised to the power 2k. Okay, such that if I define R to be this ratio t of f in L2k norm divided by f in L2k norm, then what do I get? I get that R raised to the power 2k is smaller than the sum j equal 1 to k of 2k divided by 2j times r raised to the power 2k minus 2j. Now that's a relationship between the powers of this number r's. Now we need to show that r is bounded by something independent of f, right? Because that will exactly give us a bound, well, tell us already that our map T and therefore our map P is bounded on L2K. But notice that this will follow from what we have here in star, because this, okay, this can be computed, right? This is what? This is r plus 1 to the power, if I had the sum all the way to 0, I would get exactly r plus 1 to the power 2k. And that's the expansion of that. But I don't have the term at 0, so I should subtract the term at 0, which is r to the 2k. Now you can do a bit of calculus on that. This is certainly smaller than 2k times r plus 1 to the power 2k minus 1. So now we are basically done, because if r is small, then t is bounded on L2k with norm at most 1. And if r is large, then okay, then divide by r2k on both sides of star, and you get r2k minus 1, I would say, and you get that r is smaller than 2k times 1 plus 1 upon r, which is one number below 2 times 2k minus 1. Whatever that is, sorry, so, okay, yeah, whatever that is, this is certainly smaller than 2k times 2 to the power 2k minus 1, which is some fixed number that's no independence of r and independent of f. So what have we got? And this number, by the way, is certainly greater than 1, right? So even if k is 0, then I get 2 to the minus, sorry, k cannot be 0. K is above 1, so this is 2, yeah. So therefore we have that the norm of t as a bounded operator on L2k has to be smaller than this quantity. Okay, for whatever fixed k above 1 that we are looking at. Great, so our operator is bounded on L2k for every k. But now, okay, that's t, but p is 1/2 of identity plus it. So p is bounded on L2k for all k in n star. And because p, okay, well, p is also bounded on, well, we already know that p is bounded on L2, but we've recovered that. What do we get now? We thus have that p is bounded on LP for all p in the open interval 2k to k plus 1 for all k in n star by interpolation, or by Marcinkiewicz interpolation theorem. Okay, but that then covers all of the intervals, right? Because we have boundedness on L2, on L4, on L6, and 8, and whatever, and then interpolation gives us boundedness in between these even values. So therefore, P is a bounded operator on LP for all P between 2 and infinity. And that's half of the result we wanted to prove. Now, we have to prove that P is also bounded on LP for P below 2, and that's going to be reasoning by duality. Let's have a look at it. Let's take an F that is in LP. Just to make sure everything makes sense, let's also take it in L2, and G in LP prime intersected L2, and for P below 2. So for P between 1 and 2. Right, now what can I say about the inner product of PF with G? Well defined, everything is in L2. This is the double sum n in z, m in z of f e n, p f e n g e m e n e m. But now, of course, e n e m, I have an orthonormal basis. This is 0 unless n is equal to m. So I get the sum for n in z of p f e n times g e n. But then p f e n is 0 unless n is a natural number. That's the definition of p f. And then it's equal to f e n whenever n is a natural number. So this is what that is, and this is certainly equal to the sum for n in z of f e n p of g e n, right? Because that also is equal to g e n whenever n is in n, and equal to 0 whenever n is negative. So that will be the same reasoning equal to f p of g. So I've just proven here that on L2, P is a self-adjoint operator. But because of that, I can really exploit duality to prove boundedness on LP for P below 2, because I know boundedness on LP for P above 2. And let's see how that works. Man, I can look at this integral, right, the integral of Pf times G by Hölder, and by the fact that P is self-adjoint. So this is the integral, let's rewrite it as an integral. This is smaller than the integral of f times p of g. And then I can use Hölder to deduce that this is smaller than the LP norm of f times the LP prime norm of p of g. But I know that p is bounded as a map acting on LP prime. And so what I get is this norm times the norm of f in LP times the norm of g in LP prime. Now, because LP prime is the dual of LP, or maybe more precisely because LP is the dual of LP prime, so LP is LP prime star, right? I get that the norm of P of f in LP, identifying with the dual of LP prime, has to be equal to the supremum of Pf tested on G for all G in LP prime that have norm 1 in LP prime. Right, but this inequality here, let's call it double star, I've only proven it, I suppose, for f and g in LP intersected L2 and g in LP prime intersected L2, but then, you know, this extends by density. I can take a limit. If I have a generic g in LP prime of norm 1, I can approximate it by element in LP prime intersected L2. So, you know, finite trigonometric polynomials in particular. And now what I've proven in 2 star tells me that this has to be smaller than the norm of P as a bounded operator on LP prime times the norm of f in LP, which is exactly telling me that P is bounded on LP. All right, now that concludes this proof of the theorem by Riesz, showing this very nifty proof by Bochner. Now I'd like to attract your attention to the fact that this last argument that I did, this duality argument, that is extremely generic, right? Whenever you have an operator which is self-adjoint on L2 and is bounded on LP, you usually can deduce that it's bounded on LP prime. So in these arguments, you often have to show things only on one side of 2. So either you run a L2 and L infinity bound and you interpolate, or an L2 and a weak type 1,1 bound and you interpolate. Sometimes, like in the case here, you don't have good endpoint bounds for p equal 1 or p equal infinity. The question actually about what happens to p at the endpoint p, this capital P, the Riesz projection, at the endpoint p equal 1, little p equal 1, and little p equal infinity is much harder. This gets you into the theory of Hardy spaces. So we don't have that, and Bochner realizing that, okay, you don't have that information at p equal 1 and p equal infinity, but knowing the interpolation theorem, decided to get information at L4, L6, L8 and things like that. And you could do that because these different norms for even powers have this relationship between them. So that was the very smart argument that we saw at the beginning, and pretty counterintuitive, I suppose, to start with. Right, so keep that in mind nonetheless, that you can exploit interpolation to fill in the gaps of what you don't know, for which values of P you don't have boundedness, and usually you only have to work on one side of two if you have self-adjointness through a duality argument like the one we've seen here. This is really a glimpse at the interaction between functional analysis and other sort of more hard analysis forms of analysis, so harmonic analysis in particular. And this is very common in applications of functional analysis to PDE, that you have to run arguments such as this one. All right, but we're going to leave this example here and go back to the development of our abstract functional analytic theory.